Make sure I got everything ready to rock. Yeah, it looks like. Here we go. So let's see, intro to networking. So what exactly do you guys want to get out of this class? It's really I'm gauging it for somebody who's kind of going for a CCNA. So we have such a short time frame here, just a couple hours, hour and a half, whatever. It's not enough time to actually fully teach anybody anything. Unless I was going for one narrow focused subject. And this, it's more of an overview. It's going to kind of jumpstart you, kind of get your brain working in different directions, maybe kind of show you some potential of different things, and hopefully solidify some concepts in these different routing protocols, how everything works. And this is going to be more of in-depth basic how these things work, That's what I'm going for here. So let's see how this works. I just kind of ripped off this from my old one, so not all these terms are probably going to get used in the same ways, but we'll see how this goes. So layer X, whenever I'm talking about layer something, I say that a lot. Layer 1, 2, 3, 4. That's generally as far as I go. Sometimes I'll say 7. I'll lump most of those together. We'll talk about that in a minute. Layer, I'm talking about OSI model, the Open Standards Interconnect Reference Model. And we'll go over that in detail, unfortunately. I know you guys hate it. Every time you hit anything network related, they slap you in the face with the OSI, but there's nothing for it, And so I'm no different. Talking about VLANs, that's going to be virtual LANs in reference to 802.1q. Layer 2 markings on traffic. It's really, we're going to get into detail on that. That's going to be ways to just L2 segment traffic up. Trunking, that's going to be carrying these VLAN tags from one switch to another, to keep all that intact. Outside and inside. Usually when I say outside, I mean the internet side. When I say inside, I'm talking about your juicy middle, your LAN side, where all the good stuff lives. And generally when I'm referring to it, I'm talking about NAT. In Cisco specifically, you designated an interface as IPNAT inside and one as IPNAT outside. Well, it doesn't necessarily have to be one of either. It can be multiples. But that's how it knows which direction to NAT. You tell it inside and you tell it outside. Let's see, next slide. We've got NatPat, again, network address translation. That's where you take a private IP or a subset of IPs and you translate them to public. So we're going to get more in depth. That's why I'm just kind of hitting these loosely, because as I'm going, I may mention them beforehand. I want you to kind of have a loose idea. I'm sure most of you guys are familiar with these concepts. DHCP, Dynamic Host Configuration Protocol. That's where a server of some kind out there assigns you an IP automatically. You just boot up, you request an IP, it's going to hand you one. In essence, uses TCP port 67. NTP, Network Time Protocol. Probably not going to talk about that. That's just a system synchronize your time. Bridging, that's going to refer to kind of layer 2 connectivity, connecting different LAN segments together. We'll talk about that a lot more in depth when we hit that portion of the class. The OSI model, as promised. I'm sure you guys are all interested. How many of you guys have heard of the OSI model? I know Junior expressed some ignorance of it earlier. I say ignorance just because he's an ignorant kid. There's nothing for it. Alright, it's most of you guys. I know, right, dude? Just point me out. Sweet. Yeah, there's Junior. Junior's my special friend. Goes everywhere with a helmet. Rides a little bus. No. Here we go. So it's a 7-layer model. I usually go 1 to 7. I like starting at the bottom. I've got a little... I'm adding your email to our list of spam. Oh, good times. I'm on Gmail, so I'm safe. By the way, a little tidbit, Junior says that Gmail is the hardest mail to crack into, so Hotmail is actually the easiest. That's where they get their bread and butter, so get rid of them Hotmail accounts. Anyway, as you move down the OSI model, you're encapsulating traffic, as in you're wrapping it. So you have a PDU. At each level, you have a protocol data unit. So layer 7, all the information here is a PDU. Here it's a PDU, here it's a PDU. And as you move down, you actually encapsulate or wrap it. Just think of like your Freebird's burrito. You're just putting more layers of tinfoil on top as you go down. And as you come back up, you're pulling them off. Simple. And really, honestly, I lump these top 3 together, really. the application presentation session. I lump all those together just because as network guys, we're only really concerned with 1 through 4. When it hits this part, you call the PC support, although a lot of you guys are PC supports. There's nothing for it. Please don't throw sausage pizza away. Gotcha. Oh, is that what you go with that? I just memorize it. That's a good one, dude. I like that. I like that little, that was that mnemonic. That's what that's called, mnemonic device. I always just go PDNTSPA. Because when I first started working at UCS, that was the administrative password on every machine, so it kind of forced me to remember it, PDNTSPA. And I always work from the bottom up because in the network world, when you're troubleshooting a network problem, that's the way you really need to go. Bottom up is really the preferred method that I've found over my time messing with all this good stuff. So encapsulation down, decapsulation up, and we're about to get into each one of these individually. So application, that's going to be all people sometimes need data processing. Good times, Bilbo. Layer 7 application, that's going to be your HTTP SNMP. This is where your applications live. This DEM you're in right now, that you're looking at, this is a layer 7, right? So this is your PC. Yeah, well, it's long since changed. I'm pretty sure. You might find some holdovers there, Cisco. Alright, and so far less interesting. The layer 7 stuff. It does get a little interesting in the network world because now the security guys are getting a lot more control over this. If you're doing any kind of application acceleration, a lot of times your devices are going to be kind of operating in this level in some way. Excuse me. But like in Mikrotik, I'm a big fan of Mikrotik. I'm sure most of you guys have heard of it at some point or another. If you've heard me talk about it, if you've ever looked at my blog, you couldn't help but see it. In Mikrotik, you can do an L7 inspection. You can just put a regex match in there and say on HTTP GET request, the L7 is going to actually look in that data packet for matches, and so you can actually match traffic. You can then do anything you want on that traffic. It's the same in the ASA. You can do a regex statement to actually match. It's a little bit more convoluted than it is in a Mikrotik. But I'm sure they're going to work something into ASDM eventually. They don't really have anything in there that's really functional and easy to use at this point. But you can match and do whatever you want on traffic by like a GET request. So like me personally on my blog, I have a match for anybody trying to get to the admin section of my blog. I actually do a L7 and block it unless it's coming from my specific subnet. So that's a good use for that. So moving on down, presentation, and again this is going the opposite direction that I normally go when doing troubleshooting. L6 presentation, it's going to be encoding and encryption. That's going to work directly with, each one of these layers works directly with the one above it and below it. Really uninteresting. L5 session manages connections between local and remote applications. It's generally not used in the IP suite. That's kind of a holdover, I believe, from IPX, SPX kind of thing. Transport, and this is where it actually starts hitting us and we get interested in this. And anybody, let me switch back real quick. Just to ask you guys a question, at layer 4, does anybody know what the PDU is actually called? Like, at layer 4, what's that piece of information called? It's got a special little name. Anybody? Type it in. Datagram? Totally wrong. It's a good try, though. By the way, I'll ridicule you if you say the wrong thing, so feel free to go ahead and throw something out there. Anybody? Nobody? You suckers. It's called a segment. There you go, Jacob. Segment. Layer 4, it's called a segment. This is where your TCP UDP is. Connectionless oriented. So everybody knows that TCP is a connection oriented protocol. It actually does the three-way handshake. It's gonna do and we'll actually go over that here in just a second. UDP is going to be connectionless, as in I'm just going to spit it at you and I don't really care if you get it or not. It's best effort. Here you use ports to keep track of conversations, like TCP port 22 is what? Yeah, good times, Jacob. And then say TCP 21 is what? Come on, guys, chime in. Pay attention. See what you got. There you go. Nicely done, fellers. Mark should know this. He's been jacking with FTP here for the last day or so. Yeah. And you generally use UDP ports as well. It's just a way for applications to know which traffic's destined for them. You know, it's like, how else would you know? And as we said, PDU at this level is a segment. Oh, here's TCP, a little bit more in there. Connection oriented, reliable, blah blah blah. An example would be FTP traffic, SMTP, HTTP. Another thing I like to say about TCP is that it's a really stable protocol. You know, it's made to be reliable, and as proof of that, BGP, Border Gateway Control Protocol, is basically what runs the internet. You know, that's what all your routes get advertised back and forth with, and it actually runs on TCP. I believe port 179, and so its underlying system is TCP, which means if it's gonna hold up and control the internet, it's got to be something really reliable. And so that's probably my best example for why it's such a good protocol, such a great protocol. Flow control. How much traffic can the receiving end handle? You know. And then window size is how much information you can actually pack in before you get an acknowledgement. Let's see, three-way handshake. If I'm the web server and you guys are going to try and connect to me, first you're going to send me a SYN packet. I'm going to send you a SYN ACK. You're going to ACK, and then we're established. That's the three-way handshake. 1, 2, 3. Pretty simple. When does this actually come in handy? If you guys are ever going to be doing any troubleshooting, which you will at some point, you're going to install a tool called Wireshark. Wireshark is basically a traffic sniffer, and it's a terrific tool. You can mirror report on a switch or just check traffic coming to and from yourself, and you can see what's going on, you know, with the traffic. If you know the TCP handshake, how it actually works, you know, it makes it a lot easier to disseminate what's going on and stuff, because you'll see the send and the receive. You'll see all these packets. If something in the chain breaks, you'll see it and you'll understand why. If you get a lot of retransmits, you'll know you're losing traffic. You know, if you see something send UDP one side and you don't ever see it arrive on the other side, you know, there's loss. You know, there's a lot of different things. Before, I've diagnosed MTU issues a lot with this. Diagnosed what was it? Content filtering system at the far end was actually dropping connections, and we were able to tell that because it would immediately get a response back, and it was too fast for the web server, so it was actually the content filter at the local site dropping. Let's see, UDP, again, connectionless. You just fire hose it at them. If it gets there, it gets there. Best effort, that's going to be your TFTP, RTP, you know, like your VoIP traffic. All of the conversations are actually just UDP packets flooded unidirectional. So let's see here. That's why sometimes in voice, if you've got a network issue, only one person, RTP, real-time protocol, that's going to be voice traffic in a VoIP stream. That's why sometimes if there's a network problem, say like with a firewall or something like that, you'll make a call, and that's going to actually establish through the call manager. But as soon as the call gets established completely, it cuts the call manager out, and you're just going phone to phone. So in effect, you've got phone, phone. Here's the call manager. When the call first establishes, you go to the call manager, and he's the one who actually establishes the call, right? So you ring to the call manager, and the call manager then in turn sends the ring over here. As soon as it establishes, you actually make that connection right there, and you cut out the call manager altogether. He's not even in the loop anymore. And so you're just streaming your UDP traffic back and forth. And what happens is, you know, I'll have a firewall somewhere in this chain right here. I've got a firewall right here, and he's blocking the UDP traffic going this way, so you'll only hear one side of the conversation. So this person will never hear you, but you'll hear them, you know. And so that's kind of something I've seen before with UDP, which is interesting because it's not connection oriented, so it doesn't care, you know, if you're not you're not acknowledging anything back. It's just sending it. So if something blocks it in the path, you'll never know. And that's one example. You know, only single-leg conversations, and I've had that problem before. Some of them were personally caused by my firewall rules. TCP versus UDP. TCP packets are sequenced. Again, part of the reliability is when they send, they put a sequence number on there, and you want them to arrive in sequence. UDP doesn't care. TCP is reliable. UDP doesn't care. TCP connection oriented. UDP again doesn't care. It's pretty much the same thing down the line. Virtual circuits, acknowledgements, windowing, flow control, none. So UDP is definitely best effort. L3. So what's the PDU at level, or rather layer 3? What do you guys got for that? PDU layer 3. Anybody? Good job, Baggins. Packet indeed. Layer 3, it is a packet. Layer 3 is where our networking lives. Or rather, it's our network layer. It's where our IP addressing lives. So whenever you put that IP address on your equipment, you're doing it at layer 3. It connects LAN segments, as in you've got a subnet here, and you've got a subnet here, and we put our nice router in between, and that's how we get those guys to communicate with each other. Two separate subnets have to have a L3 device in between to communicate with each other. You have to have some kind of routing device in between. Protocol numbers live at L3. That's an L3 facility, as in TCP is going to be protocol 6, I believe. Let's see, OSPF uses protocol 89. All that good stuff. We already said that the PDU at this level is a packet. Let's see here. More on the protocols. ICMP 1, TCP 6, UDP 17. So if you ever want to firewall, your ESP or AH, which are used for IPsec encryption, for that initial handshake, you're going to want to allow these actual protocol numbers. It's not a TCP or UDP port, it's a protocol number. You have to remember that and keep that in mind. As again, GREs, it's a protocol. It's not like TCP. It's not running like a TCP protocol. This is this is its own protocol number. Again, yeah, don't confuse TCP ports and UDP ports with protocol numbers. They can get a little kind of funky, hard to remember sometimes. L2 is your data link. I'm going to go ahead and tell you that at this, the PDU is called a frame, because I think I forgot to put that on here. It is a frame. F for frame. Put a circle around it, makes it super. Yeah, my handwriting's horrible. Anyway, this is where your MAC addressing lives. Media access control address. And this is also where the ARP protocol runs. People have kind of argued that that ARP is technically layer 3, but it's not really, because if you look, ARP doesn't have a protocol number, which means it's not really a layer 3 facility. It provides services to layer 3 is what it really does. So when you've got is reverse ARP layer 3. Reverse ARP is really a layer 2 function as well, because that you've got a MAC address and you're looking for IP, and that's more used like in frame relay and stuff like that. It's not really anything most of you guys are ever going to see. And so ARP is actually you've got an IP address and you need to figure out. You've got an IP address and you need to figure out what the MAC address is to send it on a local segment, and we'll get into how that all functions here pretty soon. But just know that right now it operates at L2. Moving on, the physical. This is the easy one. It's where the electricity happens. This one is going to be like your cabling standards, all that good stuff. This is where hubs go in the OSI model. We're going to talk about hubs in a second again. frame transferred to electricity and sent across a wire. This is all your ones and zeros, man. This is where the magic happens. Layer 1. But I generally, when I'm troubleshooting PDNT SPI, I work my way up. Hub's evil. Indeed. Ooh, we've got a message saying that my mic may be a little... Oh, we got a hot mic here. Hot mic. Let me see, is that better? I moved it up towards my nose, so hopefully it'll be a little bit more nasally. I also tend to talk loud. I have voice modulation syndrome. Alright, excellent. So here we go. Switches versus hubs. So I'm hitting you guys with the L2 before we hit the L3. So intro to networking. The CCNA books and stuff cover more heavily the routing because, man, that's what they do. They route a lot. And that's kind of what they're known for, although I love their switching, line. But to me, it seems more logical to go L2 and then L3, whereas most of the CCNA books go the opposite direction. But whatever, I'm different. I'm trying to be unique. So switch versus hub, what's the difference? Special indeed. Switch is at layer 2, hub's at layer 1. They only operate electrically. So what is a hub in essence? A hub is an electrical repeater. So if you've got a hub, every port that plugs into that hub is just a dumb electrical connection. What it does is it takes anything you direct towards it. Let me switch you guys over to the whiteboard real quick. Oh man, cool. I still got a bunch of old stuff in there. Clear all pages. There we go. So a hub is a guy right here that's got several ports coming out of him, right? You got PCs. Man, these are gorgeous PCs right here, let me tell you. I really got to bring my pen tab to work. And I've got a piece of traffic that I need to send to number 1, and this is number 3. So what happens is on a hub, this traffic comes in to this port and gets electrically sent out every single port. It doesn't care where number 1 is, it just sends it to everything, which is the unfortunate part of hubs, is there's no intelligence, so traffic gets out of control, right? So what we do is we compare that to a switch, and what a switch does is it's going to, no, I want those arrows, man. Let's just clear it, baby. Clear it. So a switch is going to take those ports and it's going to build what it's called a MAC table or a CAM table. If you're Cisco, it's a CAM table or a MAC address table. I mean, it's called pretty much the same. And it's actually going to keep track of where those MAC addresses live because it's all layer 2, and at layer 2 we've got our MAC addressing. So every device actually has a burned in MAC address. It's also called burned in address a lot of times. And so, you know, PC 1's going to have MAC address 1, and this PC 2 will have MAC address 2. Obviously they don't look like this, but just for the sake of saying, he's going to keep a little table in here that says 1 is out that port and 2 is out that port. So if, and conversely 3 is out that port. So if 3 sends a piece of information destined for port 1, or rather PC 1, it's going to hit this CAM table and say, oh, you're destined for 1, and then he's going to head that direction. Simple, right? So it keeps everything clean. Let's switch back over to the slides real quick, like. So we've got every port is a single collision domain, and what that means is hubs. Oh, oops, I skipped one. Hubs are half duplex, and what that means is it's only got 2 wires, and so it can only send and receive. It can only send one thing at a time. Rather, it can only send or receive at a single point in time. It can't send and receive simultaneously. So what happens is in my hub network is, I'll just go ahead and break it all down in here. In my hub network, if I'm sending a piece of information at the same time, PC2 is trying to send me a piece of information, what happens? There's a collision. It uses carrier sense multi-access, like collision detection or detection avoidance. That's what it is. And so what happens is if it sees that collision, they'll both do this standoff where they'll wait a random amount of time and they'll both try and send. And so you can imagine as your hub network grows more and more, my hub network gets huge, I end up with, you know, hundreds and hundreds of PCs. You know, nobody's going to be able to really send reliably at any time. Your bandwidth just shrinks down because there's so many collisions on the network. Everybody's having to do this TCP standoff, and it just gets hairy, right? And so what a switch port does, or a bridge port, is each single individual port is a collision domain. Because they're full duplex by nature, they can send and receive at the same time. So there's no opportunity for collision on any switch port. So you're never going to get a collision on a switch. So they scale so much better, right? And that's where all that good stuff comes in. That's why switch is good, hub's bad. Yeah, not needed, but carrier sense multi-access collision detection, right there. So, who knows what duplex wireless interfaces are, like wireless networks, by default? What duplex is a wireless connection? Half, indeed, Baggins. My little hairy hobbit friend, they are half duplex. Most people don't think about that, but on your wireless interface you can only send or receive at any one point in time. You can't do both. You'll get a collision. So it's very, it can be very limited. So wireless networks don't generally scale so well beyond, say, you know, 20, 30 clients, somewhere around in there. You know, your bandwidth's really going to degrade. It's going to go down a lot. But there's ways around that with Mikrotik in particular. Because if I'm talking wireless, I'm talking Mikrotik. I'm not going to talk about Cisco. Your Mikrotik, you can do something called dual in-stream, where you designate one of the wire that you have. You can do dual in-stream where you have two wireless cards in a single device, and you send on one card and receive on one card, right? And so it kind of treats the two cards as if they're a single interface. And so on either side of your hops, you know, you're sending with one card and you're receiving, and on the far side you're doing the opposite. And so you in effect get a full duplex link. There's also ways to kind of, there's a way to use say like OSPF. I thought WiMAX was full duplex. Let's see, like with the 802.11n with the MIMO stuff, it's still not full duplex unless you're doing send and receive specific. That's kind of where they get a speed boost. I mean, they're doing a lot of optimizations, some protocol optimizations, but they have multiple antennas, one specifically for receive and one specifically for send. That's kind of how they are getting those higher speeds. But yeah, but like you can do two wireless cards on a single device, and you can do OSPF, and you can just use costs on your OSPF links. So you can say, you know, only send out this one interface, and then only receive just using OSPF costs, you know, and selective routing. That way, in effect, you're only sending on one interface and you're only receiving on the other. And so the good thing about that is you achieve the same results as you did with dual in-stream, although dual in-stream actually does protocol optimization, so you'll get a little bit more speed out of it. But with OSPF, if you lose one of your wireless cards, the routing will converge and it'll use just a single link. So your routing will still exist. In dual in-stream, you lose a card, the in-stream link fails altogether. So kind of some pluses and minuses there. Coming back to what we were talking about, switch good, hub bad, right? And it's like it's weird to think people would even buy hubs anymore when switches are so dirt cheap. And when I say switches, I'm not talking about your unmanaged Linksys that you're buying at Best Buy. I'm talking about a good solid switch, you know. 2950s are really old, but you can get a 48-port 2950 for I think $175 from cablesandkits.com. That's where we buy a ton of our refurb gear. And so you've got the full, you know, I mean, you got the CLI. You're not going to have your L2 security features, but if you want to do good solid aggregation, I mean, you can't beat that price. It's ridiculous. Even 3550, 48 port 3550 with all the L2 security features you'd ever want. You know, to protect your DHCP servers. Same shameless. I would love a lucrative kickback. The 3550, you can do DHCP protection, and you can do man-in-the-middle protection as well. So you can really lock your networks down. With those guys, in a 48 port, I think is like 270, 300, right around that ballpark. So that's, I mean, you just can't beat those prices. It's ridiculous. Plus GBICs, if you're doing fiber backhaul, a multi-mode GBIC is going to cost you $25, and that'll kick you like 4 miles. So back to switch world, because we're kind of done with hubs. We're going to forget about that. Bridging versus switching, and bridging and switching. What are they? What are the differences? You know, because if you read the CCNA book, they'll talk about how bridges came along, and then bridges eventually turned into switches. Well, they generally don't really talk about what the difference is. And what the difference generally is, a bridge is software. Bridge is software based. In the beginning, they didn't have a lot of ASICs. Bridging was, new at one point, and they did it all in software. So everything was processor switched, which means it works great. It's just a little bit slower. So, it's not going to be able to keep up speed-wise. Excuse me. And when they talk about switching, that generally is referring to ASICs, application-specific integrated circuits, made to offload those switching features. So it's all done in hardware. It's all done speedily. So let's see. Bridges were introduced to connect two segments in a hub environment. Yeah, I mean, the idea is you have this huge hub environment that's just, you've just got crap flying everywhere. You've got collisions like mad. So what do? You put a bridge right in the middle, and so then it cuts your collision domain in half. I mean, that's, think if you have 400 machines on the same collision domain, you cut that down to 200. Your speed boost is going to be noticeable. It's going to be remarkable. And back in the day, a bridge was going to cost you an arm and a leg, so you only got one here or there. Well, what's a switch in effect? It's a multi-port bridge done in hardware. That's really the difference there. Let's see, blah blah blah. Bridges usually in software. Yeah. Okay, here's a little Mikrotik thing for you. A little point, because I like to compare the Mikrotik and the Cisco. Mikrotiks, you can create a bridge interface in that guy, and bridge ports together. You can bridge your wireless card to an Ethernet port, or bridge multiple Ethernet ports in there. Well, what are you doing? You're creating a software switch. So you're not going to get the throughput and the efficiency that you're going to get with a hardware switch. Now, they've actually started building router board models that have switch ASICs built in. That's going to be your 400 series. Like your 450s, and now the new RB750, which I did a speed test on a while back, which is pretty cool. But supposedly the switching interfaces on those guys, if you turn on the hardware switch, you can actually get, they're saying around 95 megabit of throughput. So you can see your throughput when you do it in hardware, it's going to be so much higher because the processor isn't taxed. It's pretty much cut out of the equation. So let's see, Cisco's been in the ASIC game since it bought the Catalyst series switches, and Cisco's well known for this, and I'm sure they're going to continue. Whenever they see something they want, they just go buy it. So Cisco is basically a router company. They bought Catalyst switching line. They brought was it Tsunami Networks, I think, for their wireless. The phone system, the call manager, was a product they bought. The PIX was a product they bought. Their VPN 3000 concentrators used to be Altiga Networks. They bought that. Their access control systems, they bought it. So really, very little seems to ever have been developed by Cisco, but they would get it and they would refine it and put iOS on it and sell us a whole lot. I don't know, Sweat Martin. So that's really your difference between your bridging and your switching. Cabling. We'll just talk about that really quick. Everybody knows what a straight through cable is. That's what you connect your PC to a switch. Everybody's heard of a crossover cable, but when do you use it? Switch to switch, host to host. A router is considered a host. So a router and a PC appear the same to a switch. So router, crossover cable, host to host, PC to PC, crossover cable, switch to switch, crossover cable. Now there is a concept called MDI, MDIX, which is like media dependent interconnect. I can't remember exactly what it stands for, but what it basically does is it's auto crossover. It'll electrically sense if your cable needs to be crossed over. And all of your Mikrotiks, I believe, or all of the models I've ever used have MDIX built in, which is a good thing and a bad thing. You know, sometimes people can't stand to see dangling wires. And so if there's a dangling Ethernet cable and there's another port, sometimes somebody will just take that Ethernet cable that's dangling and they'll plug it into an Ethernet port, which if your switch is MDIX, it's gonna auto sense that cable needs to be crossed, and then you'll create a loop in your network if you're not doing some kind of avoidance. Or if it happens to land on two different switches, and the STP domain isn't connected, it may throw a loop, which is not a good thing. So MDIX is not always a great feature. Cisco, I believe, didn't introduce those until the 3560 line. You can actually turn that on, but it's not on by default. Hosts or routers and yeah, there you go. So let's see, cabling. And anytime you guys have any questions, just jump in there with a chat and hit something up. You may be a few seconds behind, but I'll still gladly answer your question. Type A or B standard. Type A, old way of doing it. Type B, new way of doing it. You get a straight through cable as long as you cable it the exact same on both sides. The standard doesn't really mean anything. You can put it in whatever order you want. As long as it's the same on both sides, it's going to work. Now I'm going to say stick to the standard, just because if somebody comes in after you, they're going to look at this cable and say, oh, well, this is why it's not working, and it's jacked up, and they'll recable it the right way and it'll really not work. So stick to a standard. There's your crossover. Pretty straightforward. Let's see, 1 gig crossover. Most people don't realize, and I've talked to cable guys who that's their bread and butter, didn't realize that there's actually a gigabit crossover. There was a special crossover just for gigabit cables. So, and I've seen that personally in the field at UCS when they were running out the Cisco switchover. They were going from a D-Link infrastructure to a Cisco infrastructure. There was actually a D-Link at the leaf. A little bit higher up at the distribution aggregation was Foundry fast irons, and then it came back to big iron Foundry big iron core, but they were changing all that for Cisco. And when they were doing their cross connects, all the edge leaf switches were cross connecting into a 3550 12G, all on copper gigabit ports, and they weren't making them gig crossover, so they wouldn't actually come up as gig interfaces, and they couldn't figure out why the speed was so crappy between them. It took a TAC call and I think a few days, and they got it figured out that what they needed to do is recable these as gigabit crossover cables. And as you can see, you just take the browns, you shift them to where the blues were, take the blues, you shift them to where the browns were. You don't actually swap the pin order like you do in a regular crossover cable. Bow. Cisco Layer 3 model. This is really just for the CCNA type of guys. You got your core distribution and access, which is, you know what, generally in the Cisco world, it's more of a legacy design. You don't really see it. I mean, it's not really that true to life anymore, just because their equipment has become so powerful. This was really designed back when, they were running on 1700 routers that you were lucky if you could get 3 or 4 megabit through these things, right? So you really had to optimize them as much as you possibly could. Although, funnily enough, this is actually kind of the model that Mikrotik's moving towards with their MPLS thing. And here I'm going to digress for a second on Mikrotik's MPLS. I've got to do it because I went to the Mikrotik user meeting, and they were talking about how they were coming up with all these options, because they've been pushing MPLS, as multi-protocol label switching, which you really only see in carrier backbones. I mean, it's a buzzword, but a lot of people have heard on it. It's basically a way to take layer 3 traffic and turn it into layer 2 forwarding with tags. And I couldn't figure out why they were pushing this, because this is like a huge provider backbone type of infrastructure upgrade that you would do to someplace. And what it turns out is they're using it for the performance boost, because Mikrotik does everything in processor. because they don't really have any ASICs of their own. So what they do is, if you're running a regular routing table in a Mikrotik, something comes in, it's going to hit the processor to see where that traffic needs to route, and then it'll go out. And with MPLS, what it does is it takes that layer 3 lookup and it compiles that into like an M-tree table. I'm not sure exactly what they're doing it with. M-tree is actually a Cisco terminology. That's how they do it. But they're basically compiling it so that something comes in and it's just a quick layer 2 forwarding decision, so you get a performance boost. And I've seen the numbers. They actually are getting a pretty good performance boost out of it. And the funny thing they said is that this is new, and nobody really has any optimizations like this, and blah blah blah, which first made me scream in my head, because I'm not going to interrupt these Latvian guys. I don't know what they're going to do. I don't know if they're going to freak out and throw kolaches at me or something. But they said, yeah, they said that, and so in my head I'm screaming, Ceph, man, Ceph. Cisco came up with fast switching. It's called route once, switch many. This was ancient. This was when it was processor based for them. This technology's been around, forever, wherein it hits the processor, routes once, and then every subsequent packet in that same flow just switches through. It follows that same path. And then they came out with Ceph, Cisco Express Forwarding, where it's all hardware based now. It takes the route table, compiles that into ASICs, and it's sitting there in hardware. It's using two tables. It's using the fib and the adjacency table. Adjacency basically just says, if you're going out this interface, this is the MAC address you're looking for this IP. Takes all that stuff, compiles it into the fib, forwarding information base. So if you've got a route lookup, it's all done in hardware, man. So it happens instantly. It's done, right? And so when you run MPLS in Cisco, you're running MPLS on top of Ceph. So you're not really getting any performance boost because they're already doing everything in hardware. So Mikrotik is using this as a performance boost, and they'll lead you to believe that nobody else is doing it, but Cisco's been doing this in hardware, baby, for the last 10 years. So don't even believe the hype. They've been doing it since 95 at least. So that's me on my high horse about them saying that nobody else has done this. That just drives me crazy when these guys say this stuff. Anyway, me coming back. So now we're going to talk about IP addressing a little bit, and a lot of people use a different analogy, but I've always liked the post office model, So the aggregate network address. I'm assuming most of you guys are roughly familiar with how IP addressing works. We're going to talk briefly about subnetting. I'm going to give you kind of the ghetto workaround, the way I subnet with my fingers in my head, and the way I think most people do it in the real world, which is the quick way. But anyway, when you're talking about IP addressing, how does it get from point A to point B, and why does it do it? So the aggregate network address is like your zip code. It gets you to the right post office, which is going to be like your hey, Corey popping in. I see him up there in Canada. Those guys that put mayonnaise on everything. So yeah, so zip code. So it's like your zip code, man. So when that's going to be like the /21 that you live in, or the /16 that your addressing is in, because everybody's IP addressing lives in kind of geographical blocks around the world. So like the United States has a block, right? So if somebody in Asia wants to send it to your zip code, your /16 that you exist in, it's going to shoot it towards us. The network portion is going to be like the mail truck to come to your community, right? So my addressing, once they hit the United States for the /21, or rather the /16, the /21 I actually live in is here in Texas or whatever, in this data center that I work out of. So it's going to get there, and then the IP information is actually going to be delivering it to my mailbox, like my host address, the host portion. I think I have a breakdown of that. IP address classes. I was thinking, let me scroll through real quick. There we go. I should have moved that IP address structure up a little bit, but we'll talk about it here. The IP address structure is going to be, it's all good there, Corey. For the example of, and I'm going to use mostly /24s and below, because that's generally what people work with day in and day out. So that's going to be what's most familiar to you guys. This 192.168.0.1, that's my IP address, and my subnet mask is 255.255.255.0. Network portion is going to be 192.168.0. How do I know that? Because my subnet mask is telling me that. The host portion is the .1. Yeah, and there's a subnet mask. Yeah, oh, and it's determined by the subnet mask. There you go. And there's a good straightforward way to understand that, like in binary, all this good stuff. But I don't bother. I do it. I just do it in my head. It makes so much sense, and it's faster. And we'll get to that in just a second. Let's head back this direction so I can cover these slides missed. IP address classes. They broke these up ages ago, I guess, when they were inventing the internet. Them and Al Gore, you know, they got into this big powwow. So your class A is going to be 0 to 127, and I'll tell you guys how to kind of memorize all this stuff a little bit later. It is a good bit of memorization. There's nothing for it. If you know the subnet blocks, kind of the way they go, it's 128, 192, 224, 240, and 248. As the way they break down is, you know, as you can see, it goes to 128, and then from 128 to 192 is where it's, you know, it goes all the way up to that, and then 224 and 240. So you can see that it actually follows those blocks. Class A is going to be your giant chunks. B, C. So C is going to be your /24s, all that good stuff. Class B is going to be 16 bits. And that actually has to do with the subnet addressing, and I'll talk about that in a minute. Multicast traffic is going to live in your 224, and then experimental. I don't even know what experimental stuff lives in there. I guess whatever you kind of wanted in there to be. Special addressing, RFC 1918, everybody's heard of this. It's your private addressing, you know, the stuff you use for NATing that lives inside your network. Every Linksys router has 192.168.0.1 in there. And as you can see, anything 192.168.anything.anything is private addressing. It's not internet routable. You hit an internet route table, and it's not going to go anywhere. It's just going to drop unless you NAT it to something publicly routable. Again, with your 172.16 to 32, and then your 10. 127.0.0.1, as a lot of you know, is going to be your IPv4 loopback address, which means your local machine. You ping 127.0.0.1, it's going to ping your local machine. There actually used to be some attacks for 127.0.0.1. Now that I'm thinking about it, you could form your own packets and send them at somebody, you know, onto a subnet or something, and you could flood a subnet of pings coming from 127.0.0.1, you know, and so then they would respond to themselves or something like that. Let's see. Example IP is 192.168. Oh, we already talked about that junk. How to subnet. Here's some good resources. My favorite way to really learn how to subnet, and I had to read this guy's chapter on subnetting 3 times, but it was terrific, is Todd Lam's Cybex CCNA book. And I happen to have Googled Todd Lam's Cybex, and I may have seen some link referring to it popping up. Maybe some way to look at it online or download or something. I have no idea. And here's a couple of other, a few other resources you can use. I'm not going to get into the nuts and bolts, man, because we just don't have enough time for it. But I'm going to show you how to subnet on your fingers and in your head. Those other guys will show you how to, you know, do the binary method, which is great, and it helps you understand it. But it's not fast, and it's not efficient, and that's what I'm about. Get it done quick. So, I actually hear somebody messing around their mic. Give me just a second. Let me disable their audio. And let me disable this guy's audio. There we go. Alright. So, what's important when you're subnetting? There's only really a couple of questions you ever ask yourself is, how many hosts do we need on our subnet? So how many machines do you want to live on this subnet? You know, and you've always got to remember, whenever you create a subnet of any size, you're going to lose 2 IP addresses, one for the network address and one for the broadcast. So one at the very beginning, one at the very end. You always got to remember that. And how many different subnets do we need? So if your ISP hands you a /24, you've got your database servers, right? So we get our /24. Wow, that looks terrible. We got our database servers right here. We've got our front-end web servers right here, and then we've got our users, right? And so you've got to figure out what to do with this addressing. With a /24, how many IP addresses do you get? Who knows? Anybody? How many IPs do you get with a /24? There you go. There you go. 256, 253. Correct, man. It's technically 256. Then you're going to lose 2 for network and broadcast. So we've got a whole lot to work with right here with our /24, right? So we've only got really 2 public subnets. I've got maybe what? Let's say we've got 3 database servers, and we've got 10 web servers here on the front end. And we want to keep these separate. And we definitely want to keep the users separate from anybody else, just because I don't ever trust the users. That's the way it goes, man. And so 3 database servers. We may scale up to, I don't know, let's say that we're going to scale up to 8 at some point, right? And so we've got 10 web servers, and we may scale up to 24 at the most, right? So how do we want to divide these subnets up? Obviously we see we only really need 2 public address subnets. This over here, our users, we can just make them private. You know, we can use RFC 1918 space. You know, 192.168 something 10 or 172.16, whatever. It's because there's no sense in wasting our public addressing on these users, so we're not even going to consider them in this equation. So really, we've got 2 subnets that we're worried about. We've got we'll say 256 addresses because we got 1 big subnet. We'll just say we've got 256 routed to us. And so 8 addresses, that means we're going to need to look over here at this chart. And what this chart is, we're looking for 8 addresses. And so right here is the subnet value. So in your subnet mask, it'll be 255, 255, 255 dot something. 128, 192, 224, 240, 240. That's going to be part of our subnet mask. And then right across from it is the number of IP addresses you're going to get in that subnet with that subnet mask, right? You'll get 128, you'll get 64 IPs, you'll get 32, you'll get 16, 8, 4, 2, right? And this is the number of bits to add onto the subnet mask if you're doing slash notation. So this is slash notation. So if you wear a top hat and you've got really terrible long hair, this is your notation. Anybody get that reference? Is that too horrible? Alright, so that's your slash notation right there. So we said we're going to scale up to 8 IPs, right? But you got to remember that you're going to lose 2 for your network and broadcast. So 8's not enough. We're going to have to go up to the next block size, which is going to be 16, which means our subnet size, Buckethead Nation, yeah. Alright, so that means our subnet size for the database is going to be 240. So that means we'll be 255, will be 255, 255, 255.240 for those database servers. And then for our web servers, how many do we say? Max 24. You got to look. The largest block, or rather the smallest block that will accommodate our slash, or rather our 24 addresses, is going to be 224. And if you want to figure out the slash notation, you know that IP addresses run in octets, right? Which means you've got 4 little blocks of 8 addresses. So you've got 8 bits in here, 8 bits in here, 8 bits in here, and then you got 8 bits here. That's the way it works in your subnet mask. So it'll be your 255, 255, 255, and then 255 if you've got all ones in your bits. So everybody knows binary, right? So binary is going to be 1s and 0s. So if you've got all 0s, I figured I'd end up having to do this. It's really 1, 2, 3, 4, 5, 6, 7, 8. Alright. So it goes 1, 2, 4, 8, 16, 32, 64. That's just the way binary works. It doubles as you go to the left. And so slash notation, you've got all 8 bits set to on, because these are all off. If you set one to on, if you set them to on, all of them on, you get 255. So class C notation, or slash 24, is going to be 8 on, 8 on, 8 on. So that's class C is all of those ons. That's going to be a slash 24. So if you've got a slash 24 with a subnet mask of 240, 255, 255, 255, 240, that's going to be 4 bits more than a slash 24. So that'll be a slash 28. Slash 28 right there, right? And this one's going to be 255, 255, 255, 128. So that's going to be 8, 16, 24, and then you'll add 1 to it. That'll be a slash 25. You guys know all this good stuff because you're super subnetting geniuses. But this is the way I work in my head. I know I need 16 addresses, right? So what do is I'll hold up my pinky finger and I say 128. Then I'll hold up my ring finger and I say 64. You just divide by half. So you start at 128. So you go 128, 64, 32, 16. Alright, so I've got 4 fingers up. So what I do, I go back over to my subnets and I say, okay, and then I count 4. I go 128, 192, 221, 240. So I know that's what my subnet mask is, 240. That's how you do the finger method. So number of IPs I need, you just start throwing your fingers up as you go down. You start at 128, and then you do the same thing over here. And you can do it vice versa. You got 240. You just count how many fingers it takes to get to 240, and then you start 128 divided by 2. And then what you always remember is you always start at 128. Now it's unavoidable. You've got to remember this chart. You've just got to memorize it. Straight memorization, which I hate doing. There's very few things that I memorize, but the subnet values are 128, 192, 224, 240, 248, 252, and 254. Just saying it repeatedly and using it all the time. It's the only way it's going to stick. And that's just something you got to memorize. Another cool trick, if you don't want to do the finger method and you have the subnet mask and you want to figure out how many addresses there are, you can take 256 and divide it by that last octet in your subnet mask. If it's 224, or not divide it, but subtract it. 224, you subtract it from there, and then I'll tell you how many hosts are in there. So I get 2, 3, 32 hosts. That's just a quick tip. So let me clear off that slide a little bit. Yeah, memorize it. Unavoidable. Counting your fingers. Remember, they both start at 128, and then you just work your way. Subnet values, you work your way up. IP numbers, you work your way down, like the total number. Recount same finger, subnet values. Yeah, that's basically the finger subnetting. That's how that works. Like I said, we just don't have time to completely go over subnetting. Otherwise, I'd go over the binary method, which I totally dislike because it's so slow. It's so much easier to just do it on your fingers in half the time. And we can come back to this right at the end if any of you guys want to. I threw in one quick example for finger subnetting. I need a small subnet that only has 28 users. Let's find a subnet on our fingers to make it happen, and we'll come back to that. We'll come back to that at the end. I just want to make sure that we have enough time to get through all this material. So, variable length subnetting mask, VLSM. That's a concept that basically refers to being able to use the slash notation to refer to a subnet beyond its boundary. So if you think about it, we can go back a few slides actually to the class slides. Where are you at? Classes. So class C is going to technically a class C is always a slash 24. And this is at classful boundaries, mind you. And this is 16 because it's the number of bits, right? And this is a slash 8, right? But with variable length subnetting mask, I can say 192. I can say 192.168 if I want to. I can say 192.168. 0.0/16. That's a valid variable length subnet mask right there. And what that basically says is, because the /16 is going to be 255, which means all of these bits right here, all these first bits stay the same, and then the next bits are all 255, so that means all of these bits stay the same, and then 00 means any. So it means anything 192.168 gets matched by this rule right here. So that's a variable length subnet mask. Because a class C, which 192 technically falls under, is a /24, but we can use variable length subnet mask to go ahead and cover that whole chunk of networks. What else do we have here? CIDR is usually referenced when you're talking about BGP tables. It's really just uses variable length subnet mask to aggregate blocks of networks together. There you go, into non-classful blocks. Subnet 0 is a Cisco term that basically, if it used to not let you use the 0 portion of a subnet. So if it was 192.168.0.0, that was technically, back in the day, that was invalid. And you could use IP subnet 0 to make it valid. Whereas nowadays, that's a default command. You don't have to worry about it. That's been default since like 12.2. Let's see. Yeah, coming back to switching a little bit, to get a little bit more deeper in the way it actually works. Basic function of a switch is to connect your LAN together, right? Keep all the guys on the same L2 segment communicating. Switches build your MAC address table, your CAM table in Cisco dynamically. Wow, it's fancy. So here's the process. This is a slide I made, and I'm really boring, so I didn't use any interesting shapes or anything. But the way this works, the MAC address, the whole L2 process works, is I've got a PC. No problem, sir. The way the whole L2 process works is I've got a PC right here, and I got a PC right here. As you can see, subnet or IP address 192.168.1.1, 192.168.1.2, right? They're on the same L2 segment, they're connected, and they're on the same L3 subnet, so they can communicate with each other without having to go through a router. So, how does this work? PCA says, okay, I need to ping 192.168.1.2. So what he does is, your PC keeps an ARP cache. So what he's going to do is he's going to look in his ARP cache and say, hey, do I have this MAC address for this IP address? If he doesn't, he'll send out an ARP, which is basically a broadcast packet. That broadcast packet, as you see, is that ARP request is just going to dump out. It's going to hit this. It's going to flood every port. Well, first it's going to check the MAC address table. Do I have that in there? Yes or no? You know, if it doesn't have it, it's going to flood it out every single port it has. Which a flood basically means send it out every port, save for the port it came in on, and it's going to keep going until it reaches PCB, right? PCB will then respond and say, hey, that's me, and he's going to send back the ARP request acknowledgement saying, hey, that's me, I'm that guy, and it'll come back to him, right? Now say I've got him in my ARP cache, but both of these guys lose their power and come back, right? So their CAM tables are empty, MAC tables are completely empty. That's what we're going with. I know we're going to operate into the guise of I know his MAC address or whatever, and so it's going to come in, right? So his table is clean. So in step 1, what's going to happen is, yeah, it's going to blah blah blah. It's going to jump over here, right? It's going to hit this switch, and the switch is going to say, it's a broadcast frame, and what do I do with this? I'm going to flood it out, you know, that ARP request, and so it's going to send on. And so step 2, you see, right here, it added the MAC address into the CAM table. It said, okay, well, this guy came in, this MAC address came in port 1, so that's where that MAC address lives, right? So then it moves on to the next switch. Next switch says, I got a broadcast frame, I'm going to go ahead and flood that out every port, save for the one that came in on. And in here you see step 3, my PC1's MAC address jumps in this MAC table because it wasn't in there before, hits this guy and says, hey, that's me. and it hits the return trip, right? And it basically does the same thing. You know, your MAC address wasn't in my CAM table, so I'm going to go ahead and add, you see, number 5 entry there. And it just works its way back. That's how the CAM table is dynamically built. Now, the CAM table would get overrun if it didn't occasionally time out these entries. So if a computer, for some reason, is quiet for a really long time, his MAC address can fall out of a CAM table, and it'll have to go through this learning process again, which is normal operation. Now, CAM tables also have a finite amount of space, which is an interesting concept. So if you have a CAM table on a switch and it fills up, what happens? It's interesting. I have a CAM table and it's full. What happens? On a Cisco 6500, I believe every L2 VLAN has 256,000. It's either 256 or 128,000 MAC address limitation, and there's a lot of tools out there that can actually overrun a CAM table or a MAC address table. And what happens is when your MAC address table gets full, generally by some kind of attack, your nice fancy 6500 turns into a hub. Every packet that comes in, it sends it out every single port, you know, because its CAM table's full, so it can't actually keep track of what goes where, especially when it's full of bogus information. So if you flood somebody's switched infrastructure, not only is it going to overrun this, but it's going to overrun this, and so it's going to turn your whole nice fancy L2 switched infrastructure into a whole bunch of hubs, and you can sniff anybody's traffic or really just bring a network kind of down to its knees. So that's an interesting thing you can do with MAC address tables and CAM tables. You can flood them, and that's where some L2 security comes into play. You know, for really any kind of environment, corporate environments. You're an apartment complex. You know, you want to protect your equipment. That's something, you know, you should probably think about at some point. ARP spoofing, indeed. Samwise, ARP spoofing can be a problem. That's going to be more of your man-in-the-middle kind of attacks. And Cisco does a great job of L2 protection on that good stuff too. So we've got our switched infrastructure. We know how he basically builds his CAM table and all that stuff, but you know, what's going to keep you from creating a loop in your network? You know, moving back to here, you see how these guys are cabled right here at these 2 points. Well, what happens if I also add a cable like this to these switches? So I've got 2 connections, you see here, right? Now what happens if, and this is with no protection of any kind, if this PC right here sends a broadcast packet, what happens? It comes in this port and it's going to send out both of these ports, right? Well, this switch catches that broadcast traffic coming in on this port, so what does he do? He sends it out every other port. So it goes this way. And this guy had already sent a broadcast this way, so he sends it out every port. And so you've got basically traffic looping in your network. That's what an L2 loop is. It's where broadcast traffic or flood traffic of any kind is just looping and zooming around. And as this gets faster and faster, your switch's CPU is gonna go down. Your service is gonna degrade. The only way to fix it is to go and unplug the fools and plug them back in. And that's what can happen when there's a loop in your network. Loops, L2 loops, cause all kinds of inconsistency, especially with like 6500s nowadays, because people run a lot of layer 3 and they run a whole lot of layer 2 on the same device. So you swing a loop and it's going to cause a lot of problems, man. And so spanning tree was invented to help combat those problems, right? So basically what it does is it communicates with the other switches. It first elects a root. I'm sure most of you guys have heard a little of this. It elects a root, and that guy's the master. Everybody else is a subordinate to him, and it's going to only try and keep a single leg up at a time. So like when we're running spanning tree, what it'll basically do is it'll see that there is multiple connections and it'll shut down one of these connections. That's basically what spanning tree does in effect. You can look at all these details in here. There's a whole lot in there. 802.1d was the original in 98. It had several states, blocking or disable blocking, listening, learning, forwarding. It also was really slow. and then they came out with 802.1w doing rapid spanning tree protocol, and just a minute, I'll do it. Yeah. I'll get to it in just a second, Terry. I'll get to it in just a second, dude. Just a second, I'll get to it. 802.1w rapid spanning tree protocol was developed to help pick up where some of these shortcomings were. Cisco had already come up with some fixes for that, like sorry, it's getting kind of loud in here. They came up with port fast was one thing they came up with, which basically when an access port, just a user port, since it's electrical connectivity, it'll go straight into the forwarding state. It won't go through the discarding learning state. It'll just go straight into forwarding, so it speeds things up. Okay. Yeah. And then they came up with backbone fast, uplink fast. There's just ways to speed convergence in your network. And then 802.1w actually standardized those things, which you'll see a lot, man. There's a lot of protocols that Cisco came out with that then became standards, or where a standard version was built off of that. The PoE pre-standard, Cisco basically invented it, everybody else followed it. VRRP, HSRP, Cisco came out with HSRP, which is a redundancy protocol if you have multiple routers, and VRRP was standardized off of that. So you'll see that a lot. Most equipment conforms to the RSTP standard now for the rapid spanning tree, so that's what you're going to see out there for the most part. Here's just some port roles as they compare from legacy to rapid. And then 802.1s, or multiple spanning tree protocol, which you see used less. That's only going to be in an environment where there's a whole lot of VLAN traffic moving, and what that does is it allows you to, if you have, let me switch over to the whiteboard really fast. If you have multiple switches, right, and you've got multiple connections between them, in theory you're running a whole lot of traffic. Say there's two ISPs on this thing. You got ISP over here and ISP over here. I don't know, something like that, right? You got a bunch of traffic dumping, with a bunch of VLANs. What you can do with a multiple spanning tree is you can run kind of an instance this way, right here. Let me find my line tool. There you go. You can run an instance this way and kind of an instance this way. And so you can have some VLANs forwarding this direction, and you can have other VLANs forwarding this direction, instead of just shutting down an entire link here, and just operating on this link. This way you can have both links operating at the same time, and kind of send some VLAN traffic this way and some VLAN traffic that way. That's really what multiple spanning tree was designed for. But there's also things like Ether channel, which is another thing Cisco developed, where you can bond. Bonding is what Mikrotik calls it. You can these two interfaces here and these two interfaces here are actually kind of connected together, and you can send traffic simultaneously. It almost treats them as one interface. The open standard is going to be LACP as opposed to HSRP. And that really, I kind of prefer that if you're going to try, rather than MST, because MST is kind of a convoluted configuration process to keep up with. Plus you have to inventory how much traffic's moving from this VLAN and that VLAN. With bonding, LACP or PAGP is the Cisco proprietary. It doesn't really matter, because it's gonna bond whole. You can ether channel or bond a whole lot of interfaces together and just shotgun all that traffic, so you can get 4 gigs out of it easily, and spanning tree will run over the top of this to keep everything nice and clean. Let's switch back real quick. So you can read all that detail. Man, I spent a lot of time typing on that too. VLANs are going to be ways to segment an L2 set of traffic. So you can VLAN tag things. I'm sure most of you guys are familiar with that to a degree. Inside single switch infrastructure. So what you can do is you can, let's move back to the whiteboard really fast. I'll talk about VLANs real quick. Like VLANs are going to be back to our switches. Switches. Here's a PC. Here's a PC. Single link in between. Up to the PC. And whether you know it or not, most all switches are already running VLANs. There's usually VLAN 1 internally is already running, and all your traffic's already just tagged for that VLAN. What it means is if I'm running VLAN, say 5 in here, right? I got a VLAN that's running in my switch. What I do is I set this access port to VLAN 5. So whenever this guy comes into my switch, he actually gets tagged. His packets with 802.1q, which is the standard VLAN. ISL is Cisco's proprietary, which actually encapsulates the packet. 802.1q actually just adds on to the header, or rather the frame, a little field for VLAN, and it'll stick a tag on there. So any of my packets coming this way get VLAN 5 tagged onto them, right? Say there's another PC right here that is actually going to receive the traffic, and he's in VLAN 5 as well. What it's going to do is, as it exits this access interface, it's going to strip that tag off of it, and it's just regular traffic as it comes to this guy. This guy's going to answer. As soon as it hits that port, it's going to come in and get VLAN tagged again. And so say this guy over here wants to be on that same VLAN segment. So what we do is we create a trunk port, and that's basically, instead of stripping off the VLAN tag when it exits that port, it just says leave it intact. So if it's VLAN 5 in the switch, it's going to stay VLAN tag 5 as it goes across and then into this guy. The only thing you have to remember is the VLANs have to exist on all of your switched infrastructure that are going to be transit or termination for that VLAN. Let's see what else. In the Cisco world, I'm going to talk about this because Cisco does great on switching, plus they have really great cheap switches. I've already told you about the refurb market. You can specify which VLANs go across these ports. It's also in Mikrotik. Mikrotik does VLANing too. You can create a VLAN interface, or rather you can create a VLAN and associate it with one of your interfaces is what you can do. And then if you want to have it come out another port, you just create that same VLAN with that VLAN tag on another port. And you can even create a bridge interface inside your Mikrotik that will that you can bridge those VLANs together and actually put an IP, so like an interface inside that VLAN. Anyway, Cisco does a lot of L2 stuff, like on the 3550 you can have a routed image that can bring in access VLANs. You create a VLAN interface and you can route through that bad boy, through those VLAN interfaces. Good stuff. You can also do a VLAN trunk allow to tell it what VLANs are allowed to go across trunks, so you can get really specific with them. You can do all kinds of good stuff. So let's see. PAL. Yeah, we talked about tag. Oh yeah, nomenclature. Cisco's going to call them access ports or trunk ports. So access is going to be basically where it applies the tag. A trunk port's where it gets to carry it across. In like your D-Links and your ProCurves and your other worlds, it's called tagging, or tagged or untagged ports. So an untagged port is a port going to be like an access port where it strips the tag and goes out. A tagged port is going to be like a trunk port where it carries the tag. So there's a little bit of a nomenclature there for you. Let's see, moving on. Routing. Routing's basic job is to connect two subnets together. Every port on a router breaks up collision domains and broadcast, as in even if broadcast traffic gets sent, by default it's dropped at a router. It's like DHCP requests. If you have a DHCP server on the other side of a router, if you're doing Cisco, you have to have a helper address, which basically takes those DHCP requests because they're broadcast, and it'll send it out unicast to that specific server. Or Mikrotik has a DHCP relay agent in there too that'll do the same thing. It'll take those broadcasts and send it over. Uses a route table to determine, as opposed to your L2 with your MAC address. Use the MAC address table or CAM table. This is actually using a route table. Route process, man. How does a router work? we already kind of saw how some of that works earlier. It's basically going to, you know, traffic going to a destination. It's going to look at the packet. It's going to say, you know, is that in my route table? If the destination is in the route table, it's going to come down in here and look for to see if it's in the subnet. If it's in the route table, boom, because this guy right here, 1.2 is trying to ping 3.2. His default gateway is set to 1.1, so he's going to say, is it in my route table? Or rather, he'll say, is it on my local subnet? And he'll say, no, it's not on the local subnet, so I'm going to send it to my default gateway. He'll look at the default gateway, 192.168.1.1, pop it over to the router. The router's going to say, okay, do I have a route to this network? Yes, I do. 301, and it's going to head to that IP. Boom, next one. It's going to do the same thing, look at the route table. Do I have a route to that subnet? And he'll say, yeah, I do, and he's on directly connected interface. So what he's going to do is he's going to ARP for that guy's MAC address if he doesn't already have it. So boom, it's going to go over to the PC. PC's going to respond. It's going to go in the opposite direction. It's going to come right back. Same routing process. That's basically how it works. The way I like to look at routers is they really don't care about anybody else. They're really self-oriented. So what they'll do is, I mean, imagine a bunch of people in a line playing hot potato. They get a packet. They want to get rid of it as quick as they can, you know? And they don't really care about their neighbors as long as they don't have the packet. So they're just going to throw it at the next guy if he's the right direction to send it in. You know, they don't care 8 hops down the road. They don't care 9 hops down the road. They don't care 3 hops down the road. They just want to know next hop. That's all they care about is next hop. You know, who do I hand it to directly? You know, do I throw it to this guy? Do I throw it to this guy? That's all they care about. Building a route table. Several ways of doing it. Static, dynamic routing protocols, however you want to do it. Static routes, they can get cumbersome in a large environment. In a small environment, they're usually the best way to go. It's easy. You know, you just throw in an IP route, or in Mikrotik you go IP routes. You know, you just throw something in there. Usually, I mean, you guys are probably going to be using default route a whole lot, so you just put in your 000/0, or you know, all 0000000, and give it a gateway to throw your stuff to. Dynamics, that's going to be your RIP, your OSPF, BGP, IGRP, those kind of good stuff, made for larger scalable deployments. Their dynamic routing protocols, a routed protocol is going to be TCP or UDP. Routed means it's sent through a router. Routing means that's how you build the route table. Let's see, default route says if you don't have a match for anything more specific, then just go this direction. It's kind of your, sometimes it's called the gateway of last resort also. RIP, old school, I'm not going to talk about it too much just because it's not really used anymore. It's still around for some legacy stuff. I ran into some people running it a couple months back and they still run it. It's BVCnet in our area. It's kind of this community network connection sort of thing, and they still run it. Let's see. RIP, it was really the first guy that came around. He was in the 80s. It's really inefficient. It broadcasts every 30 seconds everything it's got in its route table. 15 hop limitations. You can only go through 15 routers rather. It's also classful, which means you can't violate that class restriction. So if I've got 2 routers together connected, and I've got 10.0.1.1/24 that's over here, and on this side I've got 10.1.0.1/24 over on this side. These routers won't route between each other. You know, if I've got a PC here that wants to go to 10.1.0.1, he won't actually be able to get there, because this router will say, you know, if they're running RIP, he'll say, oh, well, this class C, or rather this class A, is right here and it can't live anywhere else, right? It follows those classful boundaries, so you can quickly see the limitations. RIP version 2 excuse me, believe allows variable length subnet mask, so it kind of gets around that, but it's still really inefficient, and it's still got the 15 hop limitation. It does start using multicast to distribute the routes, so only people who subscribe to that information will get it, so it doesn't technically flow throughout your entire infrastructure, so it's a little bit more efficient, but still, don't bother running it. OSPF. I've got a lot in here about OSPF because it's what most people are going to run. I've got a short blurb on EIGRP, which is the Cisco proprietary, which if you're taking the CCNA, you're going to need to know that, man, because Cisco wants you to know how to use their personal stuff. But for the rest of us that aren't about to take a CCNA, I'm going to go over OSPF a little bit more. Open shortest path first. Standard based. Excuse me. It was actually... when was it made? I think in the early 90s, I want to say. There was ISIS, which was another routing protocol that was being developed, and over here in America, we thought it was taking too long, they were going too slow, so what we did is we came up with the pieces of ISIS we liked, and we created OSPF out of it, and ran it on IP, and that's where that guy came from. And so you'll actually, it's a link state protocol, concepts of areas or kind of topology limiting areas. It's a way to kind of help congestion and also speed convergence. Let's see, maintains link state database of all connections in an area. So what you do is whenever you join your router to an area, what you do is you build topology information, because that's really what OSPF advertises. OSPF doesn't share routes with each other, it shares topology information, as in everybody who's connected to an area, you know, you have a cost associated with getting to your direct neighbors, and so what you do is you share that topology information. You say, you know, my neighbors cost this much to get there, and these are the prefixes, you know, that I've got on me in these areas, and so you share that with everybody. And when everybody is considered to be converged, it means everybody has the exact same topology table. So everybody has the same view of the network, right? So what they do is they run the SPF algorithm, shortest path first algorithm, and then they build their route table based off of that information they collected. So let's see. Area 0, backbone area, everybody traverses. It's actually required in Cisco. Let's see, it's classless, which means it doesn't conform to those classless barriers. You can use variable length subnet masking if you need to. Runs distra algorithm to compute that SPF table. Uses protocol 89 to transfer routing information. Let's see, concept of DR and BDR, which can be kind of interesting for people. On like a broadcast network, like a regular Ethernet network, you elect what's called a designated router and a backup designated router. And what that's for is if you have 10 routers on there and everybody's communicating with each other, it can get kind of noisy, so they elect a designated router, which is kind of the speaker for the group. So whenever you're gonna relay your topology information, you actually send it to the designated router, and then he relays it to everybody else. So he's the go-between, and then you have a backup for him. So let's see, and that can be important for like on frame relay networks. If you have a designated router, everybody has to be able to communicate with them, so you have to make sure that that everybody can communicate properly, because frame relay can get a little bit weird, but there's not hardly anybody that runs frame relay anymore. Let's see, maintains neighbor or adjacency table. Yeah, and that's just going to be everybody who's at least in a two-way state. Now what you do is you form a full adjacency, which means you've shared all of your topology information with a designated router, but you only go up to a two-way state with anybody else, any other neighbors that aren't the DR or the BDR. What that means is you've passed all the checks, you know, you make sure everything's good to establish a neighbor relationship, but you don't share any information, right? So if you see two-way in your neighbor table, don't be alarmed. It's supposed to be like that. Let's see. You've got also hello timers and dead timers. for these guys. They communicate periodically by default. It's going to be 10 seconds on your high-speed links, your Ethernet networks, and a dead timer of 40 seconds. So if you don't get a hello within 40 seconds, that peer is considered dead, and it's going to drop that link. Slower links like your T1s or your serial interfaces are going to obviously be 30 and 120. Moving on, router types. You got a backbone router, which means only lives in area 0. Area border router, which means it straddles 2 areas. It's going to have at least one interface in 0 and at least one interface in something else. Area, or rather, autonomous system boundary router, ASBR, is going to be somebody who brings in routes from outside your domain. Link types, man, I'm going to go over these really fast. Type 1 is generated by every router sent to the DR if there is a DR election on your subnet, which is going to be your topology, your topology information. Type 2 is going to be generated by the DR, and that's sent out to list everybody in your network. Type 3 is whenever you straddle 2 networks, you're, say, connected to area 0 and connected to area 1. So right here is area 0, right here is area 1. Whenever I'm relaying area 0 information over here, I'm going to send to type 3, which is a summary. It doesn't contain topology information. It's only got the IP subnet, the prefix and the cost to reach me. That's all it's really going to send over here in those type 3s. Type 4 and 5 are going to be associated with bringing in outside routes, and so is type 7. I'm going to try and skip those, maybe come back to them if we have a little bit of time. Let's see, area types. You get your standard, stubby, totally stubby, not so stubby. The idea here is standard is going to be your regular configuration. Stubby is going to be if I've got a router over here, right, that doesn't go to anybody else, and then say this one over here goes to your ISP. And this guy's your ISP right there. If this guy, he's never going to get any more routes or anything like that, you can create him as a stub, and what that does is it blocks your type 5, which is going to be any type of external information. So if you've got the full internet route table, it won't actually come to him. It'll just send you a default route instead. So instead of having 200,000 routes, you just have a single default route because this is your only way out. That's a stub, totally stubby. Says it's going to block the type 3s as well, so the locally generated routes are going to get blocked from coming in here too. Let's see, not so stubby is like I happen to have one external connection over here, that's going to be outside our AS, and there's not a whole lot of routes that are going to be associated with it. So what that's going to do is since this is an ABR, or rather an ASBR, instead of creating a type 5 like it normally would, it's going to create a type 7, right? And as soon as it hits the interface that's going to go back to backbone 0, what it's going to do is it's going to turn that type 7 into a type 5 and then send it out that way. These guys off area 0 can still kind of come in and transit that way too. And totally not so stubby area is going to block 3s and still do the 7 translation. Most of the stuff you're not going to know for the CCNA, or really you're probably not going to use it too much in your enterprise, but it's interesting. Miscellaneous OSPF, let's see what we got. Network command, a lot of people think that that's used to tell a router what IP addresses to advertise and all that good stuff. What it actually does is it tells what interfaces to enter into the OSPF process. That's all it's for. It happens to also add those to the routing table. So everything else you're going to have to redistribute, which is a way to either pull statics or something like that in. Passive interface is a way to just tell an interface not to participate in OSPF. Summarization can only be done at boundaries because you can't affect the topology information. So You know, if everybody's in area 0, I can't filter out somebody's topology information because it'll mess up my SPF calculation. I got to have it all. So only at area boundaries, you know, when I'm spitting my type 3s into somebody else's subnet, can I actually filter traffic. Virtual links allow you transit non-backbone areas to get to the backbone. Generally not recommended. OSPF troubleshooting, make sure the metrics match, timers have to match, authentication area, the main subnet. You can't actually, if you have 2 routers like this, and in Cisco it's called secondary interface. If I've got you know, if I've got 192.168.3.1 as a secondary, right? I've got that as a secondary right here on this interface, and this interface I've got 3.2 as the primary. They'll never actually come up. These guys won't be able to peer because you can't peer a primary subnet with a secondary subnet. Only primary subnets can peer together, so that's one thing to remember. Let's see. Technically, MTU isn't part of the metrics must match, but if you don't have the MTU the same on both sides, the database descriptors won't actually be able to get across the link. Your LSAs will fail in transit, so your neighbors won't actually work properly. That's another little thing to remember. IGRPs, Cisco's initial entry into the routing protocol world. It's proprietary. It was classful, which means you couldn't violate the class boundary. They came out with EIGRP, and at that point you could do it. Uses dual, it's distance vector or hybrid, advanced distance vector I should say. Has a neighbor table, you know, topology table, contains routes, not really topology information the way you would think OSPF does. And then it's got a set of metrics. You need to remember that by default it's bandwidth and delay, and they actually recommend not using the other ones. Interesting. BGP, man, this is the big guy. This is what runs the internet. Like I said, TCP port 179. Hello interval. This is a good bit of information. The hello interval is 60 seconds, and default dead timer is 180, which means whenever BGP fails for some reason, you get a neighbor fail for some reason. It'll tell you why it failed. You know, it'll say neighbor down, interface flap. Well, that means your interface went down on your side. If it says dead timer exceeded, you know that you didn't get you missed 3 hellos basically, so it's been down for 180 seconds. You know, or it'll say peer closed the session, which means the other side manually terminated the connection. Let's see. IBGP, internal BGP, means somebody in the same AS connected to you. eBGP means it's somebody from the other side. Let's see, BGP neighbors must be sourced from a neighbor statement. AS must match that reference. And when also the IP address that it's actually sourced from only has to be correct on one side, which is strange. I know that doesn't make sense, but the neighbor IP, you know, the update source where that IP is actually coming from, only has to match on one side. It's technically best practice to do it on both sides. So don't tell people that I told you you could not do it, because it's technically a best practice to do it. So go ahead and put it the same on both sides, but it will still come up. Another thing is your BGP timers, if they're mismatch, it'll actually use whichever timer is lower. That doesn't fail. Just like EIGRP and OSPF will fail if that kind of thing's off. BGP is a lot more forgiving as far as that kind of stuff goes, and it'll just use whatever's lowest. Authentication must match MD5. That's pretty much a standard. I said Cisco only supports it, but that's same for Mikrotik too. BGP doesn't technically transfer routes either. They do network layer reachability information, which is basically going to be an IP prefix and its length. BGP advertises path attributes as well, which is going to be like path attributes going to be like autonomous system. You know, the autonomous system that it's actually came for. So the AS path is going to be your most common one, which is actually used in the route table decision. So when you're going to add something to the route table from the BGP topology information, or rather the NLRI, first it's going to look, the next hop that's listed actually has to be reachable. If it's not technically reachable in any way, it'll fail, which is why in your IBGP, you know, I've got a network running IBGP, right? These are all my IBGP peers. They have to be fully meshed for one. They all have to be connected to each other. There's ways around it, but for the guides of this, we'll say they're fully meshed. Excuse me. These guys have to be fully meshed for one. If they're all in the same AS, it's IBGP, right? And also, IBGP neighbors aren't going to communicate any topology information from other IBGP. So if I learn something, if this guy learns something from him, he's not going to tell it to him, right? Because we have to be fully peered. Let's see. And so adding that information in the route table, the next hop must be reachable. So BGP is made to carry that NLRI, not local routes. So you actually need to run your OSPF or your EIGRPs, or if it's small enough, use static, but it has to already know how to get to those next hops. If it doesn't know how to get to those next hops, via some other method, it's not going to fail. It's not going to be able to add those routes. So you have to run like an OSPF when you're in a BGP environment just to get those next hop pieces of information. And in our OSPF process, that's all we have in there are interface IP addresses. So it's going to use the shortest AS path. And so when it's looking at how to get somewhere, it's not looking at router by router or hop by hop. It's looking at AS by AS, autonomous system by autonomous system. You get assigned an autonomous system number from Aaron here in North America, and all of your cloud, your whole cloud. This cloud lives in one AS, right? And so if there's a few other ASs that are connected together, they're going to look hop by hop for AS number, 1, 3. Let's say our AS number is 4. It's going to look hop by hop. So he's going to say, to get to AS4, I need to go to AS1. So that's shortest AS path, If there's 3 ASs this way, like that, he's obviously going to go this way because it's a shorter AS distance. Then it's going to prefer something it learned from an external neighbor as opposed to an internal neighbor. And if that still matches, it's going to go lowest IGP metric. And then whichever, if those still match too, it's going to go with the one with the lowest router ID. Let's see. Route advertising. It's going to do your, let's see. Oops, sorry, I got interrupted there for a second. When it advertises out, EBGP is going to tell everybody else that he's the next hop for that route. You can change that in Cisco or Mikrotik right there. And internal, it's going to keep that next hop intact. So if we're IGP peers right here, right, we're all in the same AS. And this guy right here says that he knows how to get to a specific route. This guy right here does. Whenever that route gets to here, it's still going to have him right here as the next hop, even though he's actually 1, 2, 3 hops away. He'll still be listed as the next hop if these are IGP peers, because they expect you to be fully meshed. Right? So that's another thing to keep in mind. EBGP peers also set their TTL to 1 by default. Now route reflections is a way around it. What it basically does is with IBGP peers, if you've got one guy that kind of hangs off like a little stub network, what you can say is he's a route reflector client. So all the configuration's done on the route reflector server. This guy doesn't actually know, right here, this guy doesn't know he's a client. So you basically say, anything my IBGP tells me, any of my other IBGP neighbors, send that to him. Anything he sends me, send that to my IBGP neighbors out. So it's kind of a little workaround. NAT, network address translation, you guys know what this thing is. It takes either a single IP on the inside and translates it to a single IP on the outside, which is going to be a static, kind of your one-to-one. Or it's going to take a pool of internals and send it to a pool of externals, which is going to be like you merge two networks together and they have overlapping IP space. You're going to use that there to kind of bridge the gap until you re-IP one side. Overload or masquerade, this is where you take a whole bunch of a whole bunch of internal IP addresses, generally RFC 1918, your private address, and you're going to pat those port address, translate those over to a single public IP. And let's see, still running short on time, so I'm trying to hurry. Yeah, it's going to take all these. What it's going to do is, this guy wants to go to the internet right here. It's going to take his private IP and it's going to change the source address to look like this IP. But how it keeps track of who does what is it assigns it a port number above the well-known port numbers of like 4,000. So it's going to start, actually I think it starts at like 2,000. So it'll say this guy's coming in, and it'll do the translation. It'll keep this in the table. It'll say 2,000, send from source port 2,000, and it's going to NAT it to that public IP, and it'll go out. And when it returns, it's going to be destined. You know, it's going to hit this web server over here, and it's going to be sourced from port 2000. Well, it's going to return with a destination of this IP, but it's going to be destined to port 2000. So it's going to hit this table and say, oh, well, port 2000, that was for PC 192.168.1.2, and it'll send that traffic over to him. That's how it keeps track with PAT. So you can see that eventually, I mean, you've only got 65,000 some odd ports to work with, so eventually you'll run out. So you might need multiple pools.